Hi, I'm Juyeop, and I'm excited to present our work on 3D dynamic occupancy mapping with kernel inference and Dempster-Shafer evidential theory, which we call DSK3-DOM. Autonomous robots can infer the occupancy of areas of interest with occupancy map. Occupancy mapping helps robots to understanding their surroundings and perform various tasks like trajectory planning. Our work focuses on developing an algorithm for 3D dynamic occupancy mapping. But why is there a need for such an algorithm? Unlike ground robots, aerial robots require a more comprehensive understanding of their 3D environments. Moreover, existing occupancy mapping algorithms mostly designed for 2D environments may not provide adequate occupancy estimates due to sparse density of sensor arrays in 3D space. Furthermore, if occupancy map could also indicate the velocity and occupancy status of dynamic objects, robot could perform more various tasks such as collision avoidance and target tracking. As a result, an effective and efficient algorithm for 3D dynamic occupancy mapping is required. There are several algorithms for 3D occupancy mapping, which usually infer the occupancy of 3D environments based on sparse sensor arrays. They use Gaussian process, Hilbert maps, Bayesian kernel inference. However, they are limited to static environments. Some research focuses on mapping dynamic objects in occupancy maps using Gaussian process and Hilbert maps. Other research utilizes particle filters to estimate occupancy and dynamic state of obstacle. They adopt Dempster-Shafer Evidential theory to assign particles into areas observed by sensors for efficiency. Unfortunately, they are not suitable for 3D environments due to sparse sensor measurements and huge demands of memory and computation. Recently, the algorithm named K3-DOM is presented for 3D dynamic occupancy mapping, which overcomes problems mentioned in the last two slides. K3-DOM improves efficiency by assigning particles to ridge cells corresponding to dynamic objects. Also, K3-DOM generates dense 3D dynamic occupancy maps through kernel-based inference with Dirichlet distribution despite sparse sensor measurement. Nevertheless, K3-DOM is highly based on heuristics and lacks rigorous foundation, which sometimes leads to poor mapping performance. To address these problems, we propose an algorithm named DSK3-DOM, which adopts the theoretical foundation of PhD-MIB filter and the practicality of K3-DOM. First, we theoretically extend the PhD-MIB filter. Then, this K3-DOM approximates the extended PhD-MIB filter to the Dempster-Shafer domain. This K3-DOM utilizes a new way of kernel-based inference operated in the Dempster-Shafer domain using Dirichlet basic belief assignment. Further details will be explained in the next slides. As a result, this K3-DOM has improved performance in terms of dense mapping and accurate velocity estimation. I will explain how the PhD-MIB filter is theoretically extended. The PhD-MIB filter estimates occupancy and dynamic state of each cell sequentially updating sensor observation based on random finite state theory and Bayesian inference. The original PhD-MIB filter classifies the occupancy cell states as occupied and free and assigns particles into the occupied cells. In contrast, the extended PhD-MIB filter classifies the occupancy cell state as dynamic, static, and free, leading to efficient particle assignments only to dynamic cells. This K3-DOM is an approximation of the extended PhD-MIB filter to Dempster-Shafer domain, which have two advantages. First, particles are efficiently assigned to the observed area by sensors. Second, ambiguous observation of cell state can be handled by Dempster-Shafer evidential theory. For example, when one cannot distinguish whether the cell is dynamic or static from laser measurements, Dempster-Shafer evidential theory can explain this kind of ambiguity. Like K3-DOM, this K3-DOM also utilizes kernel-based inference for dense mapping from sparse measurements. Kernel-based inference infers the occupancy states of current points near sensor measurements using kernel functions. Although K3-DOM implements kernel-based inference on the Bayesian framework, Bayesian inference cannot be applied to the Dempster-Shafer domain. Therefore, we propose a novel kernel-based inference using Dirichlet basic belief assignment, which can be applied to the Dempster-Shafer domain. This is one of our main contributions. To validate our algorithm's performance, we conducted simulation and indoor experiments and compared its results to those of the DSPH-DMIB filter and K3-DOM as baselines. Simulation experiments depicted a situation in which pedestrians and cars are moving on the intersections. As shown in the result video, this K3-DOM generated denser maps than baselines. The DSPHD-MIB filter and K3-DOM have limitations in accurately classifying occupancy states and expressing dynamic objects in occupancy maps, respectively. The ROC curves reveal a disparity between the qualitative results of each method due to differences in the evaluation standards and cell sets. This K3-DOM outperforms the baselines in terms of velocity estimations with faster convergence and lower errors. During indoor experiments, point cloud data is collected while a person works around the larger sensors. This PhD MIP filter firstly classify occupancy states, and K3 DOM exhibits trail noises near the persons. On the other hand, this K3 DOM does not suffer from such problems. In this research, we propose a novel 3D dynamic occupancy mapping algorithm called DSK3DOM that outperforms the baselines. However, DSK3DOM still has some limitations. First, it may produce first static estimation for large dynamic objects. Second, it relies on a constant velocity prediction model, which may not accurately reflect the movements of dynamic objects. Future work may include sensor fusion with radar sensor using Doppler effects and theoretical improvements. The code for DSK3DOM is available through the following link and QR code. Thank you for listening.